Hello everyone. So this week, so far we considered the problem of mobile robot localization. We looked at the localization taxonomy. We also looked at the Markov localization, and we saw a little bit on how to do this localization given a feature-based map. Right? Most of the algorithms are looking at grid-based map. Right? Now for the next lecture, we are going to look at path planning strategies for robot motion. Okay, so what do these path planning strategies mean? So path planning strategies means given a map, right, and a localization algorithm. So figure out a path, right, that is feasible, right, so that I can get from some starting location, let's say here, to some ending location, which is say in the top right corner of the world, right. So there is some obstacle here in the middle. So all of this is known to me in the map, and my goal is to find a path, a feasible path, right, starting from a given location, right, and going all the way to the destination, which here is in the top right corner, right. So here we are going to assume that the map is given to us, right, and whatever discussion I am doing will be in the context of a location based map, right, like a grid based map or anything. But then you could think of other kinds of strategies as well, right. But the thing with path planning is it is good to know the open space as well as the occupied space in the world, right, so in the map. So that makes it easier for me to plan a path. A feasible path would always take my robot through open space, right. I mean, you must have seen this in C space, how you look at avoiding collisions and things like that. So feasible path would do that, right. So I'm going to look at strategies for searching for feasible paths, and it happens that the algorithms that we will look at all actually look at optimal paths. Basically they return the shortest path to go from one location to another, and you can think of other algorithms where in more complex environments where looking at all possible pathways are not really that feasible, right. Even examining a good fraction of the pathways are not feasible. There are more probabilistic path planning algorithms, right, which with a high probability give you a good path, right, but they'll return a feasible path, right. So those are not those are for the future, so for things that you could look at later, right. So we'll start off with a very simple path planning algorithm called breadth first search, right. Breadth first search is an algorithm that was originally designed for traversing any kind of graph data structure starting from a node, right. So in our case, the graph data comes from the connectivity in the map, right. Suppose this is like my grid map, and let's say that each one of these squares is a grid, right. So I can say that each grid cell, right, is connected to 8 of its neighbors. So you can think of this as a graph where each node has 8 neighbors. So some nodes will have only 3 neighbors, right, some will have fewer, right. So this one has only 5 neighbors, right. This node has only 5 neighbors, and this node has only 3, right. And so nodes that are here actually have neighbors that are not reachable, right. So like that. So you can think of this free space here as a graph, right. And so breadth first search allows you to search for a path on this graph, right. So you can think of that each node has 8 neighbors mostly, right, and then I have one node which is the start node for me, which is here, and one node that is the end node, which is there, and I'm going to do breadth first search, right. Basically I'm going to search this graph till I get to the goal, right. So here is how breadth first search will operate, right. So given a start vertex V and a graph G, so in this case the graph would be a representation of the free space of the map, right. So basically it starts with V, right. It puts V into some queue, right. So it's some kind of a data structure queue, and as long as there are nodes there in queue, right, as long as queue is not empty, it's going to take the first element from the queue. That's what DQ means. It will take the first element, and if V is the goal, then say return, hey, I found the goal, right. But if V is not the goal, then we look at all edges that go out of V, right. So what I mean by all edges that go out of V, so in this case it will be all the 8 neighbors, right. So take a node, so it will be all the 8 neighbors that are there for that node V, okay, for all the edges that go to V, right. Then if W has, so you call this vertex W, right. So if W is already not labeled as discovered, right? Then label W as discovered. Say, hey, now I have seen W. If it's already been seen, okay, ignore it, right? But if it has not been seen before, then I'll say, now I have seen W, right? And I maintain this parent data structure so that I can actually recover the path in the once I reach the goal, right? And then I'll say that the parent of W was V. So what does this mean? That W was visited for the first time when I expanded the graph from V, right? And now I put W in the queue and I keep going, right? So when will queue be empty? Either when will this loop end? Basically the loop will end if I find the goal, or I have explored all the vertices in the graph, right? There are no more vertices for me to see. Okay, we explored all the vertices in the graph and there are no more vertices for me to see, right? So I will be saying vertex and node exchangeably to denote a cell in the graph, right? So each cell here, each cell in the free space becomes a node in the graph, and if there are the adjacent cells to that are connected by an edge in the graph, right? So I will say sometimes node, I'll say vertex. It's a common terminology in computer science. So that I'll go back and forth. Right. So is it clear? So let's look at pictorially how this is going to look like. So here is my graph. So you can think of this as a place where each cell has either 2 or 3 neighbors, right? 1, 2 or 3 neighbors, right? So this is a map in which each cell has 1, 2 or 3 neighbors. I'm starting from the cell marked green, right? So that is my start node, right? Then what I do is I first visit the node to the right, and then I mark that as visited, right? Then I'll add these 2 nodes to the queue, right? So first, when I visit this, I'll add this and this to the queue. Let me pick up. So when I first visit this node, I'm going to put this in the queue and this in the queue, both. And I'm going to put this in the queue and this in the queue. These 2 nodes go into the queue. Right. Then what I do, I look at the first node in the queue, which is this, right? So I'll pick up. I'll pick up this node in the queue, right? That's the first node in the queue, and then I will add this node and this node to the queue. But remember, this is already there in the queue, so that is the number 1, right? So this will be number 1 in the queue. This will be 2. This will be 3, and this will be 3. Okay, so I have 1, I have 2, and I have 3. So what will be the next node that I will take up for expansion? Exactly. So the node that I marked 1, right? Now what will happen in the queue? I'll have this is 1, this will be 2, and that will be 3 in the queue. So the next node I'll take up is the one on the bottom left, right? So the node that I consider will be that, and now I don't add anything more to the queue, so my queue will still have this as 1 and that as 2. I'll continue with the 1, right, and that's not going to change much, right? And then I'll go to the next one. Now what happens is the queue would have become empty, but I'm going to add these 2 to the queue now, and therefore I'll continue. I'll finish that, right? And if any of these had been the goal, I would have stopped much before, right? So here is just an illustration for how breadth first search will look at every node in the graph, right? And if there is a goal somewhere in between before this, I will find it, and it is guaranteed as long as the edges don't have any weight. As long as the edges are all having the same weight, right? Either they don't have any weight, or another way of saying it is they all have the same weight, right? Then I'm guaranteed to get the shortest path to the goal. Guaranteed to get the shortest path to the goal. So how is that? So if you suppose you remember, whenever I mark a node as visited, right? Whenever I mark a node in green, I'll add a parent to that node, right? So what will be the parent of this node? The parent of this node is that, right? And what will be the parent of that node? That is that. Suppose I want to reach from here to here. Now what I want to look at is I'll go to the the target node, I'll keep looking at the parent of the parent of the parent of the node until I reach the source node. So that is the way I'll reconstruct the path, right? Suppose I want the path from here, right, to here from here, right? So I'll keep going, and from this one I look at the parent, which will be this, and for this I look at the parent, which will be this. For this I'll look at the parent. That is a source node that I wanted, right? So given a source node, I can find the shortest path to any target node by just following the parent marking that I did in my graph, okay, that I did in my data structure. So that's basically how this algorithm will operate, right? And so it looks at every vertex and every edge at least once, right? It doesn't look at it more than once, right? Every vertex it looks at only once, and every edge it looks at only once, and therefore the time complexity is order of v plus e, right? And it needs to store the pointers and other things, right? The parent pointer and other things for every vertex, like whether it has been visited and also the parent. So therefore it requires storage of the order of v, right? And so BFS is a complete method, right? So a method is described as complete, right, if it is guaranteed to find a goal state if the path exists, right? If there is a path from the start state to the goal state, then a complete algorithm is always guaranteed to find it, and breadth first search is complete, right? But an equivalent algorithm called depth first search, where I just keep going. So if I find a node has a child, I'll just go to that child first, right? So I will not go to the other nodes in the queue. So if the node has a child, I'll keep going to the child, and then after I finish with the child, I'll come back and I'll see if there is another child to the node, right? If you think of the graph this way. So instead of so if you think of breadth first search, it went in this order, right? Depth first search would go in this order. So this node will be looked at, right, will be marked as visited only after this node is completed. In fact, this node will be marked as visited only after this node is completed. So depth first search could get stuck exploring a wrong path if it is arbitrarily deep. You know, if the path is infinitely long, right, then it will never come back and find a goal that is here. But breadth first search will find a goal that it's a finite depth, even if the graph is infinitely large. So if there exists a path, breadth first search will find it. So that is why what we mean by saying breadth first search is a complete algorithm. But the problem with breadth first search is it expands a lot of nodes. It visits a lot of nodes, looks at neighbors of a lot of nodes before it moves on to the next. Right? It expands a lot of nodes, right? For every node, it expands all its children, right? Looks at all the children, puts them in the queue before it moves on to the next level, right? And so for every level, it is going to expand the level, children of all the nodes at the previous level, even if it is very clear that it is not going to give a short path, right? So this is a little tricky, especially when I start having weights on the edges, because all edges are not the same anymore, and I would really like to follow edges that are more likely to give me optimal paths, and keep the edges that are less likely to give me optimal paths for later, right? So for this kind of weighted graphs, right, where the edges have some cost, right, so people look at other algorithms. So the most popular of this is something called the Dijkstra's algorithm. So the Dijkstra's algorithm is essentially it finds the shortest path between any two vertices A and B in a graph, and this works on graphs that have weights, right? I mean, from if you want to be more picky about it, it works when graphs have positive weights and not negative weights. But then we are talking about path planning here, right? So paths have positive cost; they're not going to have negative cost for us, and therefore Dijkstra's algorithm works perfectly all right, right? And so among all the vertices that I haven't visited so far, right, Dijkstra picks the vertex with the lowest distance, right, and calculates the distance from that vertex to each of the unvisited neighbors of that vertex, right, and updates the neighbors in distance if it's smaller. So we'll just see how it works, right? So just look at the algorithm here. At any point of time, we start off with the full graph, right? And so we have the vertex set q which has to be examined, right? Just like we had the q earlier for BFS, we have the q, right? and for every vertex we start off by saying the distance from the source to that vertex is infinity, because I don't know, right? I have not found out the distance from the source to that vertex, so it might as well be infinity. So I am just putting it at a very large distance, right? Infinity means a very large number. I mean, of course I can't represent infinity itself, right? It means that probably the largest number that I can represent in my computer or whatever, right? And then I say that the previous node in the graph, like we had the parent, right? In BFS, the previous thing is now starts off with undefined, because I don't know how to reach to V, right? And now I put all the vertices in Q. So I need all the vertices in Q, and then at the end of it, the distance to the source is 0, because I know how to get to the source. I am starting there, right? And then just like we had in BFS, I'll say with Q is not empty, right? So I'll pick the vertex in Q, right, that has the minimum distance U. Remember, what is distance? The distance U is the distance of the vertex U from the source, right? What is the cost of the path starting from source to get to U is what I mark as distance U. Now notice that at any point in the algorithm, the distance U might not be the correct shortest distance, but at the end of the algorithm, the distance U will be the shortest distance from the source. Okay. So now what do I find now? First I pick the U that has the shortest distance so far that I have estimated from the source, right? And I'll take the U, I'll examine this U now. Now U is going to become visited, right? So what I'll do is I'll take the U from Q, right? And for each neighbor of U, right? So I'll look at how far I have come from the source to reach U, right? And how much more I have to go to reach V from U. Okay, so I'll compute that. So I call that as the current alternate distance. Okay, if the alternate distance that I've computed is less than the distance I already have stored for V. Remember, I start off with infinity, but it's possible that from some other U prime I would have visited V already, right? From some other U prime I could have found out a shorter path than infinity to V, right? But now what is going to happen is, if this alternate length I computed is shorter than the original length I had for V, original distance I had for V, then I will change that. I'll also change the parent of V to U, right? Because this is the one that gives me the shortest distance, right? And then finally, after this algorithm completes, I'll return distance, and that gives me the shortest path length from from the source node to every vertex in the graph, right? Every vertex in the graph, right? That's what distance gives me. And what does previous give me? For every node in the graph, right? Previous tells me what is the previous node in the shortest path from the source to that node, right? Suppose I want to look at previous of U. Previous of U will tell me what is the shortest path, what is the node just before U in the shortest path from the source to U. Okay, so that's basically what these things are. So again, it's a little confusing, so let's look at it in a pictorial form, right? So I start off with A as my source, right? So the vertices are labeled 1, 2, 3, 4, 6, right? And I start with 1 as my source vertex, right? And 5 as my destination vertex. Remember, I was trying to get from A to B, right? So 1 is my source, 5 is my destination that I really like to get, right? In fact, I can run it on the whole graph. So Dijkstras actually gives me, it's called the single source shortest path problem. So I start off from 1, it will give me the shortest path to all the vertices if I run the algorithm completely, right? And remember, I have the full graph, right? So these numbers right now that you see are the edge weights. So 7 here means to go from 1 to 2, I have a weight of 7. That means I have to, spend 7 units, whatever it is. I have to spend 7 units to go from 1 to 2, and likewise to go from 2 to 4, I have to spend 15 units, right? So I really like to get to 5 in the shortest cost possible, right? In the shortest cost possible. And it's not immediately, just looking at it in a glance, it's not clear what is the shortest path. So we have to do some computation, right? So now I start off with 1, right? And then what I do is I look at the neighbors, right? So what are the neighbors? 2, 3 and 6, right? So I'll update the distance of 2 to 7, right? I'll update the distance of 3 to 9, and I'll update the distance of 6 to 14, because that is the path cost from going from here to there, and the previous cost was infinity, therefore I can replace it. And for all of these, right, 2, 3 and 6, I'll say the previous node is 1. Okay, the previous will be 1. Okay, now which is the node I should be looking at next? The one that has the least cost so far, right? So which will be 2, right? So I'll look at 2 next. Then I'll look at the distance from 2 to 3, that is 10, right? So the total here is 7 plus 10. So the total to get to 3 from 2 through 2 is 17, right? So 17 is more than 9. Therefore, I'll keep the 9. So the previous of 3 is still 1. The previous of 2 is 1, right? But I'll keep the distance here as 9, right? And then I'll look at next neighbor of 2, I'll look at is 4. So I have a 7 here, right? I have a 15 here. So the distance of 4 is going to become 22, and the previous of 4 will be 2, right? Remember that. So previous of 2, 3 and 6 are all still 1. The previous of 4 is going to become 2. Okay. So now and the distance of 4 is 22, which is 7 plus 15. Okay, great. Now I am done with 2, right? So what is the next node I should consider? 3, right? Because 2 has a cost of 22, 3 has a distance of 9, and 6 has a distance of 14. So next node I will consider is 3. So 1 and 2 are already been considered, so I will already completed. So I will not look at 1 and 2. I will look at only 4 as a possibility, right? So remember, 4 has a distance of 22 already. Now if I come to 4 through 3, so I'll have a distance of 9 plus 11, right? Which is 20, which is less than 22. Therefore, I'll replace the distance of 4 as 20. And what other change I will make? So previous of 4 earlier was 2. Now previous of 4 will become 3. Okay. So previous of 2, 3 and 6 are all 1. And now previous of 4 was 2 earlier. Now it will become 3, because that is the one that I have used for getting the 20 computation. Okay. Next, what will I do? I'll look at the neighbor 6, right? So what do you think is going to happen? So for 6, it is 9 plus 2, which is 11, right? And earlier we had a distance of 14. Therefore, I'll replace that for 6 as well. So I'll make it 11. And not only that, the previous of 6 from 1 will now become 3. It turns out that getting from 1 to 6 through 3 is shorter than taking the path directly from 1 to 6. Whatever could be the reason, right? So there could be slightly some obstacles here, so where I have to spend more energy to get through, while going via 1 might going via 3 might be a easier path for the robot to move, right? So whatever reason. So it's just an arbitrary graph here. So I'm not assuming any kind of triangle inequality or anything to hold, right? That could potentially be like a small ramp here, which might actually take more energy for me to consume, while going through 3 might avoid that ramp. Okay. So now 3 is done, which is the node I should look at next, which is 6. And so the neighbor of 6 that I will consider is 5, right? And because other neighbors of 6 are all done. So when you look at the neighbor of 6, so going from through 6 to 5. So 6 already has a distance of 11, right? So I don't have to go back in the past and examine. I already know how much distance I have to travel to get to 6. So it is 11. And I have to travel a further 9 to get to 5. So the total distance to get to 5 is 20, right? So 6 is done, and we are actually done completely, right? Because the other node I have to look at is 20 is 4, right? Other node is 5, but 5 is what I am interested in, right? So I have reached 5, and there is no way that I can get to 20, I can get to 4 better than 20, because getting to 5 already needs 20, and vice versa, right? So I can't get a cost of 20 better than 20 to reach 5, because to reach 4 itself I need 20, right? Now this is done, and so what is the best path to get to 5? Remember that my parent of 5, right, or the previous of 5 is going to be 6, because that is the one that I used here. So from 5 I will trace the path back, right? The previous of 5 is 6, previous of 6 is 3, previous of 3 is 1. So the path is 1, 3, 6, 5 is the shortest path to reach 5. And likewise 1, 3, 4 is the shortest path to reach 4, and the others are directly connected to 1. So I have basically computed the shortest path to reach every one of the nodes here in the graph. But then I don't have to look at all the nodes in the graph if I had a specific destination in mind. If 5 was my destination, right, and suppose there is a whole graph out here, right, I don't have to look at it because I've reached my destination. So I don't have to examine any further neighbors of 4, primarily because 4 has a cost of 20, right. So I don't have to examine anything further. Okay. So let's quickly look at illustration of this, right. So I'm waiting for the animation to restart so that we can start from there. So cut off all this part, right. So notice that we start at this corner, right. So then we start examining all these nodes. So all the red ones are the ones that are done, and the blue ones are the ones that are yet to be visited, right. And then we continue here, and then when we hit the obstacle, you'll see that all of these nodes don't have any further neighbors to examine, so they're all being stopped. And then these are all having, so the color coding is basically the distance, right. And so the redder you are, the closer you are to the goal, and greener you are farther away, and then eventually you'll reach the goal, right. So this is essentially how the Dijkstra's algorithm is going to work, right. In fact, here, since the cost is all uniform, this is very similar to A star search, but this is how Dijkstra's will I'm sorry, since the costs are all uniform, it's very similar to breadth first search, but in the case of uniform cost, Dijkstra's could potentially work very similar to breadth first search. Okay. So if you think about how long Dijkstra's algorithm is going to take, if I'm using only regular arrays to implement this, it's going to take order of v squared, because every time I have to go through it to find out what is the minimum cost vertex, right, or the minimum distance vertex every time, so that I can expand. But I can be more efficient if I use something called a min heap. That's always going to return to me the minimum cost vertex with the small cost, right, the constant cost, in which case I can be more efficient here, right. So we don't have to really worry about analyzing the algorithm for full efficiency. And of course, the space complexity is still order of v. The same things that you stored earlier, you have to store now, right? Whether you have visited the node and what is the previous node, right? So we still have to store that. So the challenge with Dijkstra's algorithm is that it always looks at how far you have come so far, right? But on the other hand, if I have knowledge about how far I have to go also, some kind of an estimate of how much more distance I have to travel, maybe I can be a little bit more efficient in my search, right. So the idea of being able to use this kind of rough estimates, guesses as to how far more I have to go, and so on and so forth, or what are sometimes called as heuristics, right, is what we use in the next algorithm we look at, which is called A star search, right. So not only it looks at the cost of the path so far, right, which we'll store in a variable called g, but it also uses what is called a heuristic to estimate the rest of the cost needed to reach your goal, right. So this heuristic we'll call as h, right. And so at any point of time when I want to select a node, right, A star selects the node that has the smallest g of n plus h of n, right. Notice that when you start at the source, right, you have no g of n is 0, h of n is the entire distance to the goal, right. When you are at the goal, h of n is 0 because you have reached the goal, g of n is the distance from the source to the goal, right. At any point in between, you would have had some distance you have traveled to get there, which is very similar to what the Dijkstra's algorithm has. But then you also have some guess for what is the rest of the distance you need to go, and A star always uses both, right. It tries to select a node n, right, that minimizes gn plus hn, right. In Dijkstra's, what did we do? In some sense, we were picking a node that has the least g of n, right. Here we look at g of n plus h of n and pick the node that has the least g of n plus h of n, right. And notice that the heuristic function is problem specific. There is nothing very generic about it. I can't just say, okay, here is a heuristic function that will work all the time, right. And the heuristic function is also goal specific sometimes, right, because if I change the goal from the top right corner to the top left corner of the room, I have to use a different heuristic, right. And we would like heuristic functions which are called admissible, right? So admissible is the key term here. So we would like heuristic functions that are admissible, right? So admissible functions are those that never overestimate the actual cost of getting to the goal. It should not say, okay, if it's going to take you say 10 units effort to get to the goal, your heuristic, it's okay if the heuristic says it takes 9 units, or even okay if the heuristic says it takes 5 units, right? The heuristic should never say it will take 12 units, right? If the true cost is 10, the heuristic should never say 12. It's okay if the heuristic says 5, right? Because that means you will explore it anyway, because you think it's better path than what it actually is. But if you think it's worse than what it actually is, there's a small possibility that you might never explore it, and therefore you might not get the least cost path. You might not get the optimal path to the goal, right? So since you don't want to miss the optimal path to the goal, right, we assume that your heuristic is admissible, right? So let's look at the algorithm. The algorithm looks a little complex, but it's not, right? It's very similar to what you had in the Dijkstra's algorithm case, except that instead of looking at the G score, which is essentially the distance from the start to the node, I look at the G score plus the H of the neighbor, like the G score of the neighbor plus the H of the neighbor, which is essentially the estimate of the distance to go. The H is initialized a priori, right? H is something that is given to you. The function H is given to you as part of the algorithm specification. So all you need to know is the start and the goal and the whole graph that you are traversing, right? And the most of the paths are similar, right? So I start off with saying that all the distance is infinity, right? And then I start off by saying all the F score is infinity, right? And then I say that all the F score has to have so the F score of the start state is the H, right? Remember I was telling you that the start state basically is all the distance to go, and the goal state is got 0 heuristic, but that comes from the thing. So, and I also start off with my G score for the start to be 0. Why is that? Because, right, I mean I'm already there at the start state, right? So there is no G score. Remember, G is the distance to the node and H is the distance from the node to the goal. Right, and then basically we just keep updating we pick the node that has the least G score plus H score, right? We pick the node that has the least G score plus H score, and then use that for expanding our search, right? So just look at this here, how it's going to work. So here is a simple graph. Right, here's a simple graph, and I have given the H score for each node here in brackets, right? So H of A is 4, H of D is 4.5, this is 2, here is 4, and here is 2. Notice that this is essentially a overestimate, right? So if you think of this, right, so if the cost is actually 5. So the overestimate part we have to delete, okay. So we are given the H scores here in brackets here. So remember that the H is actually a underestimate, only then it is an admissible heuristic. And if you think about it, so the distance from D to the goal is actually 5, if you think on the graph, right? And we don't know that yet, right? If I know what's the shortest path, is easy. But then my heuristic says it's only 4.5. Right? Likewise, the distance from A to the goal is certainly much larger than 4, but it's okay because it's still an admissible heuristic, right? So, and then these brown numbers that you see here are the actual distances of these edges. These are the weights of the edges, and so I start off at node S, right? And I'm going to compute the F score for both A and D, right? So the G score for A is 1.5 and the H is 4. And likewise, the G score for D is 2 and the H is 4.5. So I'll take the sum, right? 1.5 plus 4 gives me 5.5, and 2 plus 4.5 gives me 6.5. And therefore, I'm going to pick A as the next node to expand, right? Now I'll expand A. Now what are the nodes that I have to consider? I have to look at B, right? What will be my G score for B? The G score for B is 3.5, right? So G score for B is 3.5, so which is basically the G of A plus the distance from A to B, which is 3.5, and my H score of B is 2, so the sum of these two is 5.5. So my F score of B is 3.5 plus 2, which is 5.5. And remember, my F score of D was 2 plus 4.5, therefore it is still 6.5, right? So, okay, that's a bad thing. So now what I'm going to do, see, notice that my admissible heuristic on this path, right, is lot lesser. So I'm just being more optimistic about the distance from A to the goal, from B to the goal, while I'm being more realistic, right? So this is the correct H score, this is the correct distance, and this is more or less correct. So between 5 to 4.5, right? So the guys who are more optimistic, I'm exploring them first, but I'll eventually get to D as well, right? So what I'm going to do next is explore B. Now the two options that I have to consider are C and D, right? So what is the G score for C? It's the G of B, which is 3.5 plus 3, so 6.5 is the G score for C, and the H score for C is 4, right? So because I'm right next to the goal, right, so I can always initialize it to the correct distance, right? Therefore my F of C is 6.5, which is the G score, plus 4, which is the H score. It gives me a total of 10.5, and my D was 6.5, so I'm going to finally expand my D. So I'm not expanding my C, I'm going to finally expand my D, and therefore what do I get? My new competitors are E and C. C we already know is 10.5. What about E? E is the G score of D plus the distance, which is 3, so 2 plus 3, which is 5. So G score of E is 5, and the H score of E is 2, so the F score is 5 plus 2, which is 7, okay? And therefore I'm going to expand E next, right? 7 versus 10.5, I'm going to expand E next, and so E's G score is 5, and the distance to G is 7. Of course the H score of G is 0, so I get 7 and I have reached G, right? So now I'll backtrace the parent node. Remember we had the parent, so the parent for G was E, the parent for E was D, the parent for D was S, and therefore that's my shortest path. Okay, it's a very simple example so that you can see what is happening, right? And notice that we never expanded C. If I had done breadth first, I would have actually expanded C also before getting to G, right? But I never expand C, right? And also the problem here is because my heuristic function was a little off, right? If I had been a little bit more clever about this heuristic, right? This heuristic, instead of being 4, let's say it had been 7, right? Which is more likely, right? Already it's even 7 is an underestimate because the distance from A to G is 9. So even if my heuristic had been 7, I would have gone down this path, right? Because with this path, my total distance itself is 7, and here my H score, my F score would have been 8.5. So I wouldn't have expanded this whole path, right? Because my heuristic was a little off, I ended up doing this path a lot, right, before I got down to the correct path to get to the goal. So we'll see how this works in this particular example. Again, waiting for the start. Okay. So here the heuristic I'm using is the direct distance to the goal, like just draw a diagonal line, whatever is the shortest path to the goal, assuming there is no obstacle, right? And you can see that when I started here, it directly expanded that line because this is the shortest path to the goal, and my heuristic says that, hey, this is going to take you to the goal very quickly. Therefore, I only expanded that path, right? And now after that, I'm just going to expand this whole region behind the obstacle. But once I got to a point, notice here, now I'm expanding the whole region that's blocked by the obstacle because it's still trying to go to the shortest path to the goal. Then once I reach a point where I get a direct line of sight to the goal, right, there's no obstacle here anymore, right, it will now only go through this path. That path stops and only this is expanded, and then I finally get to the goal, right, and this is the path to the goal, right. So a large fraction, if you remember in the Dijkstras, we had expanded almost up till here, right? In Dijkstras, we had expanded a region almost up till here before we found the path, shortest path to the goal. And in A star, we are finding it while a large number of nodes are still not expanded. So it turns out that this is actually a reasonable heuristic to have. And quite often, that is what the heuristic that we will employ in the path planning problems. It's essentially the distance as the crow flies to the obstacle and to the target, and that will always be an admissible heuristic. Okay. Right. And the time complexity of A star really depends on the heuristic. How hard is the heuristic to compute, right? And the point is, if B is the branching factor, right? Branching factor is the number of neighbors that we typically on an average have. So in our case, the number of neighbors was 8, right? So the branching factor was 8, and the shortest path to the goal, let's say, is 10 steps, right? If I'm doing dumb breadth first search, I'll really be expanding something of the order of 8 power 10. It's a huge number of nodes, right? But then if I'm using A star, I can prune away a large fraction of those because they are too far away on the by as measured by the heuristic. So anything that's going to take me farther away from the goal, I will ignore, right? And therefore, something like A star, where the heuristic allows me to kind of focus my search, is a much more efficient way of finding paths, right? In fact, if you in practical algorithms, right, practical implementations, A star and for most simple robot navigation problems. So these are the kind of the workhorses, like BFS, A star, and Dijkstras are the workhorse algorithms for path planning. But in more complex environments, people prefer what are called probabilistic path planning algorithms, where you do small amounts of sample of the world to figure out whether you are going the right direction, and these return feasible paths and might be optimal, but they typically don't guarantee optimality. They return feasible paths, but they do so much more efficiently than something like A star or Dijkstras. So we have looked at multiple topics here, but we have covered these topics at a very high level. So starting from the notion of state representations and state estimation, Bayesian filters, different variants of Bayes filters, looking at measurement models, motion models, map building, localization, and path planning. And we have again touched upon these topics just to give you a flavor of what are the various things that go into building good robotic systems, right? And this, in conjunction with whatever else you have seen already in the course, should be enough to get you started, right? But no means sufficient for you to say that I know how to do robotics now, right? And more largely, the way forward is to get your hands dirty. I mean, start building small robot models and try to play around with those. Okay. Thank you.